In this lesson, we're going to learn how to solve a pair of simultaneous equations where one of the equations is a nonlinear equation. Now, before we get to that, let's go ahead and recap some of the things we've learned this unit. So we've learned that simultaneous equations just refers to a pair of two or more equations that has two or more pronumerals. When we're solving it, we're trying to find the pair of coordinates, so an x and a y pair, that satisfies both equations. If we are trying to do this graphically, we know that we can solve it by finding the intersection point of the two graphs. We know that if the graphs don't intersect, that means that there's no solution. And if the graphs intersect at every point along the line, that is, if they overlap, then there are infinitely many solutions. If both of our equations are linear equations, we've learned that we can solve using the substitution method or the elimination method. Today, we're going to try to apply these now to solve systems of equations that involve some nonlinear graphs. So, for each of the examples below, we need to do two things. We need to identify the solutions graphically, and we need to solve the system of equations algebraically. Let's go ahead and look at the first question. So in the first question, we have y equals x squared and y equals x plus 2. We're initially asked to solve this pair of simultaneous equations graphically. That means we're looking for the intersection point of these two graphs. So if I look at the intersection point of these two graphs, there are two. So this system has two solutions. I can go ahead and write down the coordinates for both of those two intersection points. So the first one is 2, 4, and the second one is -1, 1. I've solved this graphically. Now we aren't always given the graph of a pair of equations, so we need to know how to solve algebraically as well. To solve this algebraically, I'm going to examine my two equations. I'm looking for an opportunity to use the substitution method or the elimination method. I notice that in both equations, they are both solved for y. So I can take the expression that's equal to y in one equation and replace y in the other equation with that expression. So we're going to use the substitution method to solve this. When we use the substitution method, we can rewrite our equation as x squared equals x plus 2. Now this is an equation that we can solve because we have one equation and it only has one pronumeral. Now it is a quadratic equation. When we're solving quadratic equations, we've learned that it's best to start by setting the entire equation equal to 0. So I'll rearrange my equation so that I have all of the terms on one side and 0 on the other side. Now, if we can solve this equation, if we can factorize this equation, that will make it easier for us to solve. So let's see if we can factorize this equation. I need two numbers that add to -1 and multiply to -2. Those two numbers would be -2 and +1. So I can rewrite this equation as x minus 2 times x plus 1 equals 0. From here, I can apply the null factor law. So the null factor law says that either the first expression needs to equal 0 or the second expression needs to equal 0 in order for the product to be 0. I can solve both of these equations and I end up with x equals 2 and x equals -1. Excellent. I'm mostly done with the problem, but I haven't yet got the other coordinate. I know that with a pair of simultaneous equations, I'm looking for an x value and a y value. So for each of these values of x, I need to substitute them into one of my original equations and solve for y. I can substitute them into either original equation. I find the first one to be pretty simple, so I'm going to substitute both of these into that first equation. So I've got y equals 2 squared which means that y equals 4. So my first solution is that x equals 2 and y equals 4. My second equation, my second solution will be y equals -1 squared, and I've made sure to put that -1 in brackets, and that's y equals 1. So my second solution is x equals -1 and y equals 1. And I can see that that matches the solutions that I got when I solved this system graphically. Let's try another problem. Here, we're again looking at the system involving a linear graph and a parabola. We're going to start by finding the solutions graphically. So we're looking for the intersection points of these two graphs. And the intersection points are at -5, 21 and 2, 0. That's excellent if we have a graph, but if we don't have a graph, let's see how we can work this out. We can see that in the first equation, y is already isolated. That lets me know that substitution is going to be an excellent option here. I'm going to take the expression that's equal to y in the first equation and substitute it for y in the second equation. That's going to give me 3x plus x squared minus 4 equals 6. Now, since I'm just adding that expression, those brackets that I've put there don't really have any mathematical impact. Since this is a quadratic, I'm going to go ahead and rearrange the equation, and I'll put it in descending order. So I'll start with x squared plus 3x minus 4 equals 6. And I'll go ahead and set it equal to 0. So we've got x squared plus 3x minus 10 equals 0. To solve this quadratic, it would be easiest if I can factorize. So I'm looking for two numbers that add to 3 and multiply to -10. Those two numbers would be 5 and -2. So this factorizes into x plus 5 times x minus 2 equals 0. I can apply the null factor law, and I know that either x plus 5 equals 0 or x minus 2 equals 0, in which case x would be equal to -5 or x would be equal to 2. Now I'm mostly done, but I remember that for a pair of simultaneous equations, I need an x and a y coordinate. So I'm going to substitute these x values back into one of my original equations. I'm going to use the first equation, but I could use either one. So when I substitute it into the first equation, I end up with y equals -5 squared minus 4. And again, I'm sure to put that -5 in brackets. And this comes out to y equals, that's 25 minus 4, which is 21. So the first solution is -5, 21. The second solution is y equals 2 squared minus 4. And that's y equals 4 minus 4, which is 0. So the second solution is x equals 2, y equals 0. And again, that matches the solutions that I got when I solved this graphically. All right, let's try one more. So in this graph, we're looking at a linear graph and a hyperbola. We can see graphically that there are two solutions because there are two intersection points. So our solutions from the graph are the two intersection points, which are 1, 6, and -6, -1. Now, if we want to solve this algebraically, we need to be looking for an opportunity to do substitution or elimination. Looking at our equations, we see that both equations have y isolated. So we can take the expression that's equal to y in the first equation and substitute it for y in the second equation. That's going to leave me with x plus 5 equals 6 over x. Now, if I want to solve this equation, I don't want to have a fraction there. If I've got fractions in my equations, I should try to eliminate those fractions by multiplying both sides of the equation by whatever the least common denominator is. In this case, our only denominator is x. So we'll multiply both sides of this equation by x. On the left side, that gives me x squared plus 5x. And on the right side, those x's cancel and I'm left with just 6. So I'll go ahead and notice that this is a quadratic equation. If I want to solve a quadratic equation, I can always start by setting it equal to 0. So I'll rearrange the equation to x squared plus 5x minus 6 equals 0. What can we do from here? If you've said factorize, you've got that right. So to factorize, let's look for a pair of numbers that add to 5 and multiply to negative 6. Those two numbers would be 6 and negative 1. So this equation can be rewritten as x plus 6 times x minus 1 equals 0. Now, if we apply the null factor law, then we know that either x plus 6 equals 0 or x minus 1 equals 0, in which case x needs to be negative 6 or x needs to be positive 1. Now we're almost done, but we need to get a value for y. In order to get a value for y, we need to substitute our x coordinates into one of the original equations. I'm going to use the first equation, but either one would work. So I'll first substitute in negative 6, and I'll have y equals negative 6 plus 5, which is negative 1. So my first solution is x equals negative 6 and y equals negative 1. I'll then substitute in my other x coordinate, which is 1. So I'll have y equals 1 plus 5, which is 6. So my second solution is x equals 1 and y equals 6. This matches the solutions that I was able to get and observe visually from the graph. So I'm trying to solve most of the time when you have a nonlinear graph and a linear graph, you're likely going to use substitution. And if you come up with a quadratic equation that needs to be solved, try putting it into standard form, setting it equal to 0, and then look to factorize or use the quadratic formula.